Hi, I'm Luca Bartolomei, and I'm going to present you our work Active Stereo without Pattern Projector. Our code, trained models, and paper are available on our project page. Given a pair of stereo images, stereo algorithms try to resolve the so-called correspondence problem. This problem is not easy. Uniform areas such as the wall shown in the figure make the problem ambiguous. Furthermore, depth stereo networks suffer when dealing with unseen scenarios. Active Stereo deals with ambiguous regions using a physical pattern projector, which aims to ease correspondences. However, a pattern projector is not feasible in outdoor scenarios, where ambient light cancels out the projected pattern. Furthermore, active light decreases proportionally to the square of the distance. Consequently, Active Stereo cannot deal with long distances. Inspired by Active Stereo, our technique, dubbed as VPP, virtually projects a pattern into the stereo image pair, according to sparse depth measurements. We assume a calibrated setup composed by a stereo camera and a depth sensor appropriate for the final environment. Our proposal outperforms state-of-the-art fusion methods, even few depth points such as 1% of the whole image. Finally, as shown in the figure, virtual pattern reduces domain shift issue without requiring an additional training procedure. We compare our method with three different stereo and depth sensor fusion strategies. In guided stereo matching, the authors propose a framework that injects depth seeds into cost volume using Gaussian-like modulation curve. In LiDAR StereoNet, the authors propose a custom network architecture that fuses sparse depth and color information at early stages. Each modality has a unique feature extractor, and resulting feature maps are concatenated and fed into the next stage. CCV norm is a custom network architecture that fuses the previous two ideas. Firstly, color images are fused together with depth hints using concatenation. Then, in cost regularization stage, depth hints are injected using a modulator layer. As for previous methods, our proposals rely on sparse depth seed, but differential from them, we inject sparse points directly into images using a virtual pattern. For each node points, we convert depth into a disparity, then we apply a virtual pattern in each stereo image according to a patterning strategy. Our method does not require any change or assumption in the stereo matcher. We investigated different patterning strategies, starting from a baseline case where each virtual projection does not improve distinctiveness, neither improve corresponding match. In other words, this patterning technique is ineffective. Firstly, we proposed a random-based strategy that does not explicitly model distinctiveness, but we empirically proved that the strategy is effective. Next, we developed a distinctiveness-aware pattern based on analysis of scanlines. Each projection produces a side effect that must be taken into consideration. Furthermore, with the idea of increased visibility of virtual pattern, we propose in case 4 and 5 a uniform patch-based patterning strategy. However, as uniform patch-based could lead to ambiguities, we developed in case 6 and 7 a patch-based patterning technique where each pixel has its own pattern. We assume from two parallel patches also in the uniform case. We improve previous patterning technique even more, considering subpixel disparity values, deep network issues, and occlusion handling. Firstly, we propose a splatting technique to inject subpixel information into the images. Next, we develop a blending strategy to perform even better on deep networks. Occlusions are an intrinsic product of the stereo system, as each view sees the scene in a different perspective. In particular, known depth seeds that are visible in the reference view but occluded in the target view could lead to ambiguities. In this example, known point P is virtually projected according to a patterning strategy. However, as P is occluded in target view, the virtual projection covers the original foreground content Q. Consequently, foreground endpoints has no longer a clear match. If we can classify correctly P as occluded, we can exploit the potential of our proposal. Instead of projecting a pattern that would cover foreground content, we can virtually project target content of Q into the reference pixel of P. This solution is the correspondence for P and does not interfere with foreground pixel. We propose a simple heuristic to classify occluded sparse disparity points. Considering the target view, we assume at least one foreground sparse point in the neighborhood of the occluded sparse point. In conclusion, we will show experimental results against competitors and the effectiveness of our method with off-the-shelf stereo networks. As shown in the figures, VPP generally reaches almost optimal performance with only 1% of depth density. Except a few cases in a training configuration with some higher density, VPP achieves much lower error rates. These last plots show the effectiveness of our technique using off-the-shelf networks. Even without any additional training, our framework boosts accuracy of any model with rare exceptions. Thanks for the attention.